Okay, welcome back. So, as you remember, in the previous lectures, we were looking at generating function, and then we studied the ordinary generating function. So we said that we can use the ordinary generating function and solve recurrence relations and other questions about counting. And now we saw that it was very useful, and then let us look at one more example and try to solve it using the method that we know, right? So let's say that we are given the following recursion formula, right? So an is equal to n into a raised to n minus 1 plus let's say 2n, right? So it is defined in terms of an minus 1 and n, right? So an is defined this way, and n is greater than or equal to 1, and a0 is the 5 is equal to 5 is the initial condition. Now, as usual, when we have such a formula, what we do is we multiply the recurrence relation both sides by x raised to n and take the sum, right? So summation n greater than or equal to 1 an times x raised to n. And what is that? This is equal to x times, right? Because we are just shifting to take the degree sum inside. Summation n greater than or equal to 1, n times n minus 1, which is the coefficient, x raised to n minus 1, plus some 2x times summation n greater than or equal to 1, n into x raised to n minus 1, again taking one x outside. Now, what does this gives us? So it gives that, let's say that the left hand side is the first term is missing from a of x, right? If a of x is the generative function for an, then we have a of x minus 5 because a0 is 5, right? Which is the LHS. On the RHS, similarly, we have x times summation n minus 1 x raised to n minus 1 plus 2x by 1 minus x whole square, because summation n x raised to n minus 1 is 1 by 1 minus x whole square, that we already saw. But now the problem is that what do we do with this other term, right? The first term on the RHS. So we have summation n x n minus 1 x raised to n minus 1, and we don't know how to convert this to a nice formula or write in terms of a of x, right? How do you write it in terms of a of x? Because of the n sitting there, we will see that it's not easy to do that. So now why did this not work, right? So one can show that this really doesn't work. This method does not work to get a generative function, a nice generative function, because as one can verify that if you look at this an, right, this an is n times an minus 1 plus 2n. So every time it's multiplied by n, right? And therefore you will see that this sequence grows faster than n factorial. And because of this, one can show that the ordinary generative function will not converge, and then therefore we will not get a nice function as we did in the previous case. So in that case, what we will do, right? So if the function does not converge, we cannot really use the method of generative functions to do nice things. So in that case, we will do some tricks. So we are going to learn some thing, and one of the most standard way to deal with this kind of thing is to use what is called the exponential generative function. So what is the exponential generative function? Okay, so given a sequence fn, right? So a sequence of real numbers, then the formal power series f of x is equal to summation n greater than or equal to 0 fn into x raised to n by n factorial. Okay, is called the exponential generative function of series sequence. So what we have done here is that, see, we know that fn is growing, let's say, fast, right? So if fn is growing fast, I want to make the function to be convergent. So to make the function convergent, right, the series to be convergent, what I can do is to divide throughout by n factorial to make the coefficient of x raised to n to be small. Right? So if the coefficient of x raised to n is small, then one can hope to make it convergent. Right? So if I divide all the time, right, all of fn by n factorial, and then take the sum, then I still get a power series where because I am instead of summing fn, I am going to sum fn by n factorial, right? So therefore, there is a much better probability of convergence. So if fn is growing, large, close to n factorial, one can try to do this, and then it might work. So, so basically, n factorial acts as a normalizing factor, right, to make fn to be small. Now, how do you recover fn? Well, because we are smartly using with the xn, I am basically dividing by n factorial. All I need to do is to take the function, whatever we get, look at the coefficient of x raised to n by n factorial in the series expansion. That will be equal to fn. So even though n factorial may not be present, right, when we look at the coefficient of x raised to n, we get something, right? But we have to look at the coefficient of x raised to n by n factorial. So if there is no n factorial present in the denominator, we multiply both sides by n factorial and then get the denominator by to be x raised to n by n factorial. And then we will get the coefficient of that will be precisely the fn that we want. So this is something that we can do. So one can try to use the same method in the previous example, and you will see that it will work. So let's look at a slightly different example to begin with. So we have the example fn is equal to 1 for every n, right? So we take the constant sequence, even though it doesn't grow fast. I'm going to just look at this example, right? So I divide by n factorial everywhere, right? So I have fn by n factorial, summation x raised to n by n factorial, which is, as you know from basic calculus, it is the series expansion for e raised to x, right? And the reason, this division by n factorial and taking the series sum to be called exponential generative function is precisely that the constant series will get the exponential function e raised to x as the generative function. Okay, so this is the example I wanted to present you first. Now let us take another example. Okay, so we have let's say a0 is 1 and an plus 1 is defined to be n plus 1 into an minus n plus 1, okay, for n greater than 0. Find a closed formula for fn, closed formula for the generative function for the sequence an. So one can check the ordinary generative function does not work because we have this n plus 1 multiplying every time, so it grows, right? The coefficient grows very fast. So we will try to use the exponential generative function. So a of x is summation an into x raised to n by n factorial as the exponential generative function for the sequence an. So what is an? Which is defined by the recursive formula, right? So an plus 1 is n plus 1 into an minus n minus 1. So take the summation, right, by multiplying with x raised to n plus 1 by n plus 1 factorial on both sides. I will get summation n greater than or 0 a n plus 1 into x raised to n plus 1 by n plus 1 factorial, and summation n greater than or 0 a n into x raised to n plus 1 by n factorial, because the n plus 1 got cancelled. So we have actually multiplication. The n plus 1 will be multiplied by divided by n plus 1 factorial. So I will get n factorial in the denominator. Similarly, for the second time also n plus 1 goes. So therefore I get my summation n minus 1 into x raised to n plus 1 by n factorial. Okay. Now So now we can write the LHS, the first term is missing, therefore it is A of x minus 1, where the first term A0 is 1. And then similarly from the right hand side, you can see that you will get, you take one x outside, it is an x raised to n by n factorial, which is again the A of x. So therefore I have x times A of x. And similarly from the last term, you will get what x square into summation x raised to n minus 1 by n minus 1 factorial, right, from this term, and then from the 1 by n factorial I will get summation x raised to n by n factorial, right? So summation x raised to n by n factorial with x outside is x into e raised to x. Similarly, the previous term is x square times e raised to x. One can verify. I mean, it is the same summation. And the first term is x times a of x. So therefore, all these functions are known to us, right? So now I can write a of x in terms of this function. So I will get a of x is equal to 1 by 1 minus x into this 1 by 1 minus x into 1 plus x e raised to x into 1 minus x. So therefore 1 minus x cancels out in the second time. So I get 1 by 1 minus x plus x times e raised to x. Now each of these I can find the coefficient of x raised to n easily. So this is summation x raised to n, the series expansion. And the second one is summation x raised to n plus 1 by n factorial. Okay, so coefficient of x raised to n from the first one is n factorial, because I have coefficient of x raised to n by n factorial is n factorial here. Coefficient of x raised to n by n factorial is n factorial. And the coefficient of x raised to n by n factorial here is, you have to look at the coefficient of x raised to n, so therefore it will be n minus 1 factorial below, right? But then I have n factorial here, so n factorial by n minus 1 factorial will be n remaining. So I have n factorial plus n. That is the coefficient of x raised to n by n factorial in A of x, and which is the nth term. So the nth term is n factorial plus n. That is the claim. So if you want, you can go back and verify whether it is true for the values. Okay, I will not go into the verification part. You can do it. So this is how we can use exponential generative function to deal with things. So it is the calculations are exactly the same. Only thing is that instead of looking summation fn x raised to n, we are looking at summation fn x raised to n by n factorial. So another example, summation, I know an plus 1 is 2 into n plus 1 into an plus n plus 1 factorial n greater than equal to 0, with the initial condition that a0 is 0. Find a formula for n. Now, so what is the solution? So we have a of x is equal to, let's say, summation an x raised to n by n factorial, where an is the nth term of this the series that we have defined recursively. So if you look at the exponential generative function, then you can take the the recursive formula, right? The recursion relation, and then multiply by x raised to n plus 1 by n plus 1 factorial on the left side and on the right side. You will get, as usual, the terms to be exactly as before, right? 2 into summation an x raised to n plus 1 by n plus 1 n factorial, n plus 1 cancels. And from the last time n plus 1 factorial itself cancels, I will get summation x raised to n plus 1. Now this one is x by 1 minus x, because we have just one extra x sitting here. And this one is, if you take one x outside, it's basically a of x. So it's 2x times a of x. So a of x, and the first term is 0. Therefore, on the LHS, we have a of x itself equal to this. So therefore, a of x into 1 minus 2x is equal to x by 1 minus x. So I can divide by 1 minus 2x. So x by 1 minus x into 1 minus 2x. And one can verify that this is actually equal to 1 by 1 minus 2x minus 1 by 1 minus x. It's easy to do this calculation, right? So I can write it as this. And from this, I will get summation 2 raised to n x raised to n, and this one I will get summation x raised to n. That is a of x. But we want the coefficient of x raised to n by n factorial in a of x. So what is the coefficient of x raised to n by n factorial? Just multiply with the coefficient of x raised to n, right? Which is therefore n factorial into 2 raised to n minus n factorial into 1. Right? So therefore, I get n factorial into 2 raised to n minus 1 as the coefficient of x raised to n by n factorial, which is a. So I can solve questions using EGF very similar to the one that we did before. Okay, now you can take it as a homework to solve the first question that we started discussing and then fail, right? Using the ordinary generated function. Now try to use it with exponential generated function. And once you have, we can go to look at the meaning of the product. So what is the product of generative functions? So how do you define the product? The product is of course defined in the previous as before, but when it is exponential generative function, how the product can be calculated, right? So we want to see that. So let us look at the product of a of x and b of x, where a of x is summation a n x raised to n by n factorial, and b of x is summation bn into x raised to n by n factorial. So the product a of x into b of x can be defined as follows. Okay, so it is equal to summation n greater than 0, summation k equal to 0 to n, ak by k factorial into bn minus k by n minus k factorial, and then that is the coefficient of x raised to n. So therefore, the coefficient of x raised to n by n factorial is summation n greater than 0, right? And the coefficient of x raised to n by n factorial is just multiply by n factorial on the term that we got. So therefore, I will get summation k equal to 0 to n factorial divided by k factorial into n minus k factorial. Okay, this is by converting this x raised to n into x raised to n by n factorial. So to do that, you have to multiply by n factorial here, right? So once I have the n factorial, I can take these two together, right? N factorial by k factorial into n minus k factorial. A k into b n minus k, right? And this is equal to summation n greater than 0, summation k equal to 0 to n choose k into a k into b n minus k, x raised to n by n factorial, and that is equal to summation cn x raised to n by n factorial, which is c of x, right? So cn is, let's say, defined to be this sum. Okay, so if I define this to be cn, then I will get this, right? Okay, so if I define this thing in the bracket, the yellow bracket as cn, then I will get cn into x raised to n by n factorial, which is c of x for some counting sequence cn, right? Now we have to see what this is, right? So the so how did this come across? Summation n greater than 0, summation k equal to 0 to n ak by k factorial into bn minus k by n minus k factorial. Now this is easy to see, right? Because the coefficient of x raised to n comes from precisely the summation that you take the coefficient of x raised to n in the kth term and n minus kth term, right? Which is bn minus k by n minus k factorial, and then their product and sum over all k ranging from 0 to n. So therefore, this is clearly our usual product of the series, right? So two series we have multiplied and then we get this. We are just writing it in a nice form by converting it into this form, and we want, because we are looking at the exponential generative function, we want to have this as our defining term, right? So coefficient of x raised to n by n factorial is what we want. So therefore, we are converting into that form, and then we will get summation n choose k into a k into bn minus k, k ranging from 0 to n. Now we want to see how this can make sense so that Cn is well defined, right? Cn is well defined, but what is the counting sequence for which object? So what is the combinatorial meaning of the product of exponential generative functions? So we are describing the meaning as follows. So we have, let us say, An of course counts the number of ways to build type A structures, and Bn is the number of ways to build type B structures on an n element sets. Now suppose suppose A of x and B of x are the generative functions, exponential generative functions, and Cn be the number of ways to choose a subset, let's say T, of the set 1 to n. Okay, so we have the set and we want to choose a subset. So you should recall that in the previous case, right, when we are looking at the ordinary generative function, we were not choosing subsets, we were just choosing sub-intervals, right? We were not changing the orders, right? We were forced to choose in that particular sequence 1 to n. If I have the set 1 to n, I have to choose from 1 to, let's say, I plus 1 to, let's say, j plus 1 to etc., right? So therefore, there is a difference here. We are choosing a subset of 1 to n. So it can be any arbitrary subset. So the number of ways of choosing a subset T, and then build a type A structure on this set T. Okay. Now once you do this, then you build a type B structure on the complement of this set. And then, so let me try to put a nice figure. So we will see this later, but this figure may be very instructive to see. Okay, so how do I draw this? Okay, so what I want to do is that I want to choose some subset, okay, some subset of this. Then I want to put a type A structure on. Okay, so I'm choosing some subset. And on this set, I'm going to put a type A structure on. Okay. Then I take the complement, and on the complement, I'm going to put a B type structure. Okay, so given the set of n elements, I choose a subset T, put a structure of type A on the set, then take the complement, and on this set I put a type B structure. Okay. Now, if Cn is the number of ways of doing this, then the claim is that C of x is A of x times B of x, and Cn counts the number. This coefficient of x raised to n in this product counts the number of ways of doing this. So An is the number of ways to build type A structures on an element set. Bn is the number of ways to build type B structures on this. And Cn is the number of ways to first partition the set, n element set, into two parts, right? Like, one subset and its complement. And on the first set, I am going to build a type A structure, and the second part I am going to put a type B structure. And this is counted by Cn, then C of x is equal to Ax times B of x. That is the claim. So how do you prove this? Well, if you look at the definition, it should be kind of clear, because what we have here, right? Definition of product. What does n choose case say, right? N choose case is that I can choose some k element subset of the n element set. So that is the number of ways of choosing the k element subset. Now, once you choose the k element subset, then I have ak ways of putting the type A structure on the k elements, right? So because there is k element, I have exactly ak ways of doing it. So once you choose the subset, I have n choose k ways of choosing this. And once you choose the subset, I have ak ways of making the type A structure. And on the once you choose the k element set, its complement is unique. So the n minus k element set, I can put a B structure on B n minus k many ways, right? So therefore, that is the number of ways of doing this, and that is what we want, right? So therefore, it makes sense. So here is an example. Okay. So a group of let's say n students want to form let's say 3 clubs. So A, B, C are the clubs, and each student must be in exactly one of the clubs. The club A must have an even number of members, right? I mean, it could be 0, nobody can be there also. And the club B must have an odd number of members. On the other hand, club C says that I don't care whether I have odd numbers or even numbers, but there should be a president, right, for the club. I mean, we want clubs with presidents. So the club C requires that by mandate that there should be a president. Club B says that it should always have an odd number of members, and Club A says that it must have an even number of members, even if nobody is there. Now compute, let's say Dn, which is the total number of ways to do this. Okay? So, given a set of, let's say, let's set S of people, they can form a club A, right? If cardinality of S is even, right? So only when cardinality of S is even, we can form a club, and there is precisely one way to do it. They all form a club from that, right? So once you say that these are the guys going to the club, even if if it is exactly even number of members, they form the club A, right? If cardinality of S is odd, we cannot form a club of type A. So therefore, the generative function for I of x is summation x raised to 2n by 2n factorial, exponential generative function, right? Because x raised to 2n to say that we can only choose an even number of people. N can be 0, therefore n greater than 0. So I can choose 0 guys, 2 guys, 4 guys, etc. And what is this? I can write it as half of summation n greater than 0, x raised to n by n factorial plus summation n greater than 0 minus 1 raised to n x raised to n by n factorial. This is the way to split this and write this. And if you look at this, you will see that this is precisely the generative function for e of x, generative series, and similarly series for e raised to minus x. So therefore, it is half into e raised to x plus e raised to minus x. Right? That is the generative function for I of x. So we get it immediately from this form, right? X raised to 2n by 2n factorial. Okay, so yes. Now let us solve for b of x. So b of x is summation x raised to 2n plus 1 by 2n plus 1 factorial. And in a similar way, if you do calculation, you will see that it's actually equal to e raised to x minus e raised to minus x over 2. And c of x is summation n into x raised to n by n factorial, because once you have n people, you have to choose one of the presidents in n possible ways, right? Any n of them can be a president. Therefore, there is n possible ways to do when you are given a set of n guys. So therefore, I have summation n into x raised to n by n factorial, which I can write as x times e raised to x by taking one x outside, right? And this summation is already known to us. And so we have all these things, right? A of x, b of x, and c of x. And since we are looking at the number of ways of choosing a club, right? A, B, and C by partitioning into 3 parts, we can do apply the product. Right? So d of x is a of x into b of x into c of x, and which is e raised to x plus e raised to minus x by 2 into e raised to x minus e raised to minus x by 2 into x into e raised to x. So we get the generation function, and then we can look at the coefficient of x raised to n, and for that we do some simplifications which are routine, so I don't want to go into much detail, right? So this product I will write it as e raised to 2x minus e raised to minus 2x by 4, and then you have x into e raised to x, and this reduces to, right, once you take it inside, e raised to 3x minus e raised to minus x by 4, and then e raised to 3x I can 1 by 4 I can take outside, x e raised to 3x I can simplify by 3 raised to n into x raised to n plus 1 by n factorial, because 1 x is outside, coming from outside, and similarly 1 by 4 into minus 1 raised to n x raised to n plus 1 by n factorial. So the coefficient of x raised to n by n factorial is n factorial by 4, right, from here, and then 3 raised to n minus 1 by n minus 1 factorial minus 1 whole raised to n minus 1 by n minus 1 factorial, which is n by 4 into 3 raised to n minus 1 plus minus 1 whole raised to n for n greater than or equal to 1. So this is a nice way to do it.